Okay, so I suppose I'll get started. I welcome the viewers to this problem solving and live interaction session for the subject experimental stress analysis offered by Professor K. Ramesh on the Swayam portal. So today we will be discussing the contents of week 5. My name is Ganesh Ramaswamy. I'm a PhD scholar in the Department of Applied Mechanics and Biomedical Engineering, working under Professor K. Ramesh and Professor U. Saravan from the Civil Engineering Department at IIT Madras. So with that, let us get started. So let us look at the first question of the day. So the question says, the following image of a model is obtained by viewing it through a plane polariscope with the elements crossed and the analyzer oriented at 30 degrees to the reference axis. That's what is said. So essentially, the first thing is we are looking at a disk under diametral compression. So what is said is, so we have a light source. So we have a light source and let that be the light path. So we have been told that it's a plane polariscope arrangement. So essentially there will be only two polarizers, out of which one will be the main polarizer, which will be placed before the model. And after the model, we will be placing a crossed polarizer because the question says that it is crossed. So initially the conventional polariscope arrangement, plane polariscope arrangement with crossed elements is this. However, in this question, it says that the analyzer has been imparted a rotation of 30 degrees and they have been kept crossed. So essentially what that means is, so we have rotated this by 30 degrees and we have rotated this by 30 degrees and they are still kept crossed and the model comes in between and we are looking at point A. We are looking at some point A, and this is 30 degrees. This is the datum. So this is kept at 30 degrees. And in a plane polariscope, we are aware that we will be seeing both isochromatics and isoclinics in a plane polariscope arrangement. In a plane polariscope arrangement, we will be seeing isochromatics as well as isoclinics. This is sigma 1 minus sigma 2 equal to some constant contour. And this is theta 1 equal to constant and theta 2 equal to constant. Or rather, I should say theta. I will simply say theta p. Theta p is the principal stress direction. So that is equal to some constant. So these two are the fringes that we see in a plane polariscope arrangement. Now it says we are able to see that a fringe passes through the point of interest like that, small fringe like that. So it is asked what is the principal stress orientation in degrees at point A in the figure. So it is clear that we have rotated this by 30 degrees, and that is when the plane polariscope light that was coming like that, it entered, passed, because the fast and slow axis are aligned with it, it passed and it got cut by the analyzer. This is the analyzer, this is the polarizer, and this is point A, not to be confused with analyzer. So when we kept it at 30 degrees and it was crossed, the fringe passed through point A, and this is the isoclinic fringe. So therefore, the principal stress orientation at point A is nothing but 30 degrees. So this is how we can find the principal stress orientation at any point on the domain by rotating the. So what is the procedure to find theta p at any point is to rotate crossed combination of polarizer and analyzer till a fringe passes to. So that I'll just till the fringe crosses. Anyway, when I'll post this, I'll write it a little more neatly, but I suppose you get the idea. And suppose if I rotate the polarizer analyzer combination, crossed combination, and the fringes don't move, it implies that those fringes are isochromatics. Whereas if they move with my rotation, then naturally there is an angular dependence, which implies that those are isoclinic fringes. There is another way to differentiate between isoclinic and isochromatics. Let us say that we load it more. Since it's in linear elasticity, if we load it more for the same problem with a higher load, our principal stress orientation is not going to change. Whereas the principal stress magnitudes will definitely change. So what that implies is that the isochromatic fringes will move, but the isoclinics will remain the same. So these are two ways to differentiate between isoclinics and isochromatic fringes. So I hope that is clear. Should there be any questions, please feel free to ask. Okay. So with that, let us move on to the next question. The method of using analyzer itself as a compensator is called what? Now let us look at this term compensator. So essentially we are trying to compensate for something. Now when is this used? When we want to find n, that is fringe order, at some point. When we want to find fringe order at some point, at our disposal, we only have one indication that it is a fringe from the user's perspective. Conventionally, I'm saying, if we were to look at it from a naked eye, what we can see is fringes passing through points. Through a point of interest. So, if I can make the one of the fringes, a known fringe, pass through that point of interest, and I know the mathematics behind it, then I can figure out what is the quantity, what is the fringe order at that point. So that is, we are trying to artificially compensate for the retardation that has been brought about at that point. Fringes for for the fringe order, for fringe order, we are looking at isochromatic fringes. So here we compensate for the remaining retardation. That is, we have taken up a problem, we have loaded it, and we want some point of interest. We want to find the fringe order at that point. By the very virtue of loading it, the mechanics of the problem has brought about some fringe order at that point. But a fringe is not passing from there. So we are unable to make out what exactly that fringe order is. So we compensate, we provide additional retardation by some means and make the fringe pass through that point. And since we have introduced that remaining retardation, we can subtract that out, add or subtract that out, however that is, from the result, so that we get the actual fringe order at that point. This is the whole idea behind compensation techniques. So there are a couple of types. This type of compensator, Babinet-Soleil compensator, it is an external device which we will align at theta p, and then we'll try to rotate it. It basically has a glass which can introduce one particular retardation by rotation of a knob, and that knob is actually calibrated. So many rotations imply that it will bring about this particular retardation. So they have a calibration chart. So what we will do, we will align it at that point. We will rotate it till the fringe passes. We'll see what is the value of retardation we have introduced in some other metric, so that we can read out from their calibration chart as to what is the actual retardation we have added. So this is an external mechanism. Whereas if we look at Tardy's method of compensation, this actually uses the analyzer itself to carry out the to introduce the retardation, and we can simply read from why by rotating the analyzer, by rotating this analyzer, we are able to find out this angle, right? That 30 degrees. So for example, we are rotating it somehow by some angle when we actually see the fringe pass, so we can read out that angle from uh, the dial itself, and that has a correlation with the introduction of retardation. So in Tardy's method of compensation, we use the analyzer itself as the compensator, and we will see how that comes about. It has been discussed in the lecture also, but anyway, we will also see how that comes about. So I hope that is clear. Okay. So let us look at this question. To find the fringe order at any arbitrary point using compensation techniques, which of the information are required? Neighborhood fringe order, isoclinic angle at that point of interest, isoclinic angle at the boundary, wavelength of the light used. Now, naturally, when we are talking of compensation, we need to know which is the fringe that has moved. For I'm taking this example again. So, for example, the fringes are like that. The fringes get formed like that, let us say, for some particular load. And then there is a fringe like this. There is a fringe like this. Now we want to find out the fringe order at this point by compensation. This is the point of interest. Now what we do, we either by using that Babinet-Soleil, which is a component which we will place here and then rotate the dial, or by just simply rotating the analyzer, what we are trying to observe is a nearby fringe passes through that point. We know how much we have done to make it pass through that point, but we should also know what is the fringe that has passed through that point. So essentially, we need the neighborhood fringe order. What is neighborhood? Neighborhood of that point. So we will rotate it such that either this fringe or this fringe passes through that point, and then we'll suitably add or subtract to identify what is the fringe order at that point. So neighborhood fringe order is necessary. Also, the isoclinic angle at the point of interest is necessary because we need to align the polariscope. In the case of Babinet-Soleil, we need to align the compensator at that angle. For example, if the angle over there is 45 degrees, we should align it at 45 degrees and then start rotating the knob. If we were to use Tardy's method of compensation, where we use the analyzer itself as the means to introduce the retardation, or rather as a compensator, in such a case, also we need to position the entire polariscope at that angle and then go about doing our study of compensation. So isoclinic angle at that point of interest is necessary. Isoclinic angle at the boundary, it has no bearing on the isoclinic angle at some arbitrary point. So essentially, we are only focused on that point. One thing to note is generally photoelasticity is I'm sorry. Generally photoelasticity is whole field. But as soon as we come for compensation techniques, that is, we want to find the fringe order at one point, then it becomes a point by point technique. So compensation essentially is a point by point technique. Now there are other ways, newer methodologies developed to find out the fringe order over the entire domain by doing color matching, phase shifting, things like that. But in conventional photoelasticity, where it was not the digital eye, but rather the person, the photoelastician who is doing the experiment, if they wanted to find out the fringe order at one point, so essentially it became a point by point technique. The wavelength of a light used doesn't bear any consequence here. Why? Because we are seeing the fringes, and those fringes essentially are formed because of the light used. Now, light is not something that we are changing. We are only introducing retardation where this fringe will essentially move to that point. So it has no bearing on that. So essentially, we need to know the neighborhood fringe order and the isoclinic angle at the point of interest in order for us to perform compensation techniques. I hope that is clear. If there are any questions, please feel free to ask. In the meantime, I'll move forward. Should there be a question, please feel free to stop me and ask. Okay. So when compared to a plain polariscope, two additional elements, quarter wave plates, in circular polariscope help in removing which of the fringes is what is asked. So essentially, when we have a light source, and we have a polarizer, we have an analyzer, and then we have some model here that is stressed. So when we look at this, we essentially, in this arrangement, we'll get a combination of isochromatics and isoclinics. Why? Because the output light intensity is sine square 2 theta and psi square delta by 2. So it has a dependence on theta as well as delta for the case of plane polariscope. And why do we call it a plane polariscope? Because we are impinging plane polarized light onto the model. Whereas if we were to take the same case, and we introduce a quarter wave plate in between, we put it here, and then we introduce a quarter wave plate here, like that. Let this be the fast and slow axis. This be the fast and slow axis. And we position it at pi by or 45 degrees. And we position this at a higher, that is 45 plus 90. In such a case, the output light intensity. Here we will be seeing only isochromatics because the output light intensity now is I. I have kept this analyzer as 0 and it is crossed, and the quarter wave plates are also crossed. So I'll essentially be seeing Ia sine square delta by 2. So I have only a retardation dependence. I do no longer have the angular dependence. So for a circular polariscope, I see only isochromatics and I don't see isoclinics. And there is no arrangement where I can see only isoclinics. One way to one workaround we can do is we know that sigma 1 minus sigma 2 is nf sigma by h or t or whatever the thickness. In such a case, if we were to take a material with a very high stress, very high value of f sigma, if f sigma is very high and we don't load it as much, yeah, f sigma is very high and we apply very less load, then naturally there will be very feeble fringes. We will not be able to see much of isochromatics. Isochromatics will be very feeble, whereas isoclinics will be clear and rather prominent. So that way, that is one workaround where we can see isoclinics with isochromatics not disturbing as much. But there is still no way to see only isoclinics. Like we cannot remove it in totality. So with that, if we see when compared to a plain polariscope, two additional elements of the circular polariscope help in removing, which is removed, isoclinic contours are removed. So I hope that is clear. Okay. So let us look at the next question. The retardation caused by a model when a white light passes through it, if the point of interest is having the retardation caused by a model when a white light source is passed through it at the point having fringe order 0 is how much is what is asked. So retardation we know is nothing or rather fringe order n is nothing but our retardation by 2 pi, or retardation is 2 pi n. So therefore, if n is 0, naturally our retardation introduced is 0 in this case. I hope this is clear. Okay, so let us move on to the next question. To find the isoclinic angle at a point of interest, one should follow which of the following steps? Select the option representing the correct sequence. So not only do we have to identify which step is applicable, we also have to mention the sequence in which we are going to do it. Okay, so we want to find, our motive is to find the isoclinic angle. And this we saw in the very first example, we saw a crossed combination of polarizer and analyzer. This needs to be imparted with a rotation of crossed combination of polarizer and analyzer. This is how we find an isoclinic angle at a point. For isochromatic, or rather for a fringe order that comes from isochromatic data, in addition to this step, we need to go for compensation. So here we need to do this by rotating the polarizer and analyzer. So the first requirement is we should be able to see the isoclinic fringes. So naturally, we cannot go for a circular polariscope arrangement. We have to go for a plane polariscope arrangement. So 2 is correct. 2 is there, 1 is not there. Rotate the analyzer polarizer crossed combination until a fringe passes through that point of interest. So 3 is also part of our scheme. Rotate the first and second quarter wave plate combination until the fringe passes. So since we are not looking at a circular polariscope, this doesn't apply. Rotate the analyzer clockwise. Now we saw that rotating the analyzer alone is part of Tardy's method of compensation, which is required for calculating the isochromatic fringe order, not isoclinic angle. So this this does not form part of our sequence. Orientation of the analyzer gives the isoclinic angle. As we saw in the first problem, when we kept it at 30 degrees, the 30-degree isoclinic passed through that point. So the orientation gave us the isoclinic angle at that point. So 6 is correct. Orientation of the second quarter wave plate does not. So we have got 2, 3 and 6 as the correct as the process steps, but are they in the correct sequence? We can just read it once again. Keep the border in the plane polariscope. Rotate the analyzer polarizer crossed combination until a fringe passes through the point of interest. Orientation of the analyzer gives the isoclinic angle. So this is in that order only. So essentially 2, 3, 6 is correct. 2, 3, 6 is what we'll do in order to determine our isoclinic angle at any point of interest in a problem. Okay, that's great. So I hope this is clear. Okay, so let us look at this question. Different setup of polarizing elements are given in the table. Identify the background of the model for the corresponding setups. Enter D for dark field and D for bright field. Now, the first arrangement, let us look at the first arrangement. This says the polarizer and analyzer combination is crossed and quarter wave plate is not there. It says none. So essentially, we can see that this is a plane polariscope arrangement. This is a plane polariscope arrangement. So plane polariscope arrangement, when analyzer and polarizer is crossed. Let us take this example. Let us take this example. From here, we have light passing like that. And since we are looking at the background light, I'm not considering this model presently. I'm just looking at what is outside the model. For example, if this is my field of view, or rather, if my analyzer is circular, it is in this shape, let us say, and I'm free to rotate it. So inside that circle, let us say this model looks like this. We are looking at this area. We are looking at the background. And the question that is being asked is whether that background will be white or dark. So if for the background light passes through this and this is kept crossed, so what will we see as the output light? There will be nothing allowed after the analyzer. So essentially this will be dark field. Essentially this will be dark field. This is dark field because the analyzer and polarizer is kept crossed. The other ones, we are able to see that quarter wave plates have some combination. So the others pertain to circular polariscope arrangement. Okay, so let us try to work this out. One of the examples, at least, let us try to work this out. So from Jones calculus, we know that a retarder essentially can be any optical can be represented as a rotator and retarder. So, so the matrix, rather, let me say the general matrix for that is cos delta by 2 minus I sin delta by 2 cos 2 theta. This is minus I sin delta by 2 sin 2 theta. The diagonal is the off diagonal elements are same, and this just has a change of sign. This element of the matrix just has a change of sign here. So this is how we can represent a particular optical element. So what we go on doing is initially we have some light that is coming, and this light we will subsequently place our optical elements here. Optical element 1, 2, 3, so on. We'll go on placing. At the end, we are anyway going to read it using an analyzer. So at the end, whatever comes, we can take the magnitude of that and try to analyze what is the output light characteristics. So for a quarter wave plate, say at theta equal to 45 degrees. Now essentially what I'm trying to say is let us analyze the first combination here, this combination, where both are crossed. Now let the polarizer be at 90 degree. And that is what we have been following. So let that be at 90. If that polarizer is at 90, let first quarter wave plate be at let us say 45 degrees. If that is at 90 and this is at 45 degrees, the light amplitude gets split equally, and this brings about a retardation of lambda by 4. Hence, it will give a circularly polarized output. Very well. Now, this part, from this part, saying that this is crossed. 1 minute, let me take the heading also so that there is no confusion. Okay, so this is what we are looking at. This is the polarizer. This is quarter wave plate. Okay, so if the if it says that the quarter wave plates are crossed, so if this is to hold true, if this is so, then second quarter wave plate will be at 135 degrees. Crossed meaning plus 90. It is at 135 degrees. And by virtue of this, here, then analyzer will be at 0 degree. 0, 180 takes the same thing. Uh, the polarizer has its axis like this. If I place it like this or like this, it makes no difference. It is one and the same. Okay, so we know this much so far. Now, what is the expression for the quarter wave plate? Let us try to evaluate. So, for the quarter wave plate, for the first quarter wave plate, this will be delta is nothing but 2 pi by 4. 2 pi by 4, which is pi by 2. So this is cos pi. Actually, let me just make this thing a little thin. So this is cos pi by 4 minus I sine pi by 4 cos. This is at 45 degrees. We have seen here this is at 45 degrees. So 2 theta is 90 degrees. So this is cos 90. Mind you, here, please don't get confused. I am plugging in one as degree, as radian, another as degree. So when you plug it, you should plug it appropriately because these angles and the retardation is generally measured in degrees and radians respectively. I'm showing it like this. But when you plug this expression into a calculator, please be sure to appropriately put it in consistent units so that your answer doesn't go haywire. If I write here pi by 2, okay, in fact, let me write pi by 2 to avoid confusion. Let this be pi by 4. This is pi by 2. This is 3 pi by 4. And this is 0 only. So this will be cos pi by 4 into 2. So this will be pi by 2. So this is minus I sine pi by 4 sine pi by 2. This will be the same, and this will be just the opposite sign of this thing. It will just be plus. Very well. So let us see what this comes out to be. So this is quarter wave plate 1. First quarter wave plate. If we solve for this, this is cos pi by 4 is 1 by root 2 minus I sin pi by 4 cos pi by 2. We know cos pi by 2 is 0. So here also this is 0. So essentially I don't have anything here. So this will be minus I sin pi by 4 sin pi by 2. Sin pi by 2 is 1. Sin pi by 4 is 1 by root 2. So this is 1 by root 2. So this is like that. And this will be 1 by root 2. So I have a neat expression for the quarter wave plate here. It is 1 by root 2, 1 minus I and 1. So this is for quarter wave plate 1. Similarly, for quarter wave plate 2, you can plug in and see it will be just this expression except at that is at 135. So it will be plus. So that will just be positive. So far so good. So we have got the expression for both the quarter wave plates. Now let us say now we have to analyze this combination, crossed combination. So let our arrangement be like this. Polarizer at 90. Then I have fast, slow. Then I have analyzer is crossed at 0. So for this, let the input light be some k omega t. Now I have to represent this by the first, I have to pass this through the polarizer. Polarizer is allowing only along the y-axis. So it is 0, 1. Then I have the first quarter wave plate. First quarter wave plate, I put it here before that. Then there is no model. Why? Because in this problem, we are looking at the background light intensity. So there is nothing, no model in between for now. And then we have the second quarter wave plate. I have the second quarter wave plate placed here. Then I have my analyzer. Analyzer is at 0 degrees. So analyzer can be represented as, in fact, let me put it here. For analyzer at beta degrees. For the analyzer at beta degrees, the matrix is nothing but cos beta minus sin beta, cos beta. Once we put this, its first component, beta, E along beta is this, E along minus beta is this, E along minus beta plus pi by 2 will come out to be this. So when we place an analyzer at some beta angle, what we need to do is we need to multiply what comes out of the second quarter wave plate with this matrix, which will bring it to our normal basis. After that, intensity of light at minus beta is what is the light that we will see, essentially. So this is what we need to place here, except in our problem, beta is 0. Why? Because our analyzer is kept at 0 degree. Because our polarizer is kept at 90 and we are solving the problem where polarizer analyzer is crossed. I hope that is clear. Let us simplify this further. I'll just do one example in detail so that you at least know what it entails. After that, we can go for some this thing. Okay, so let me do it step by step. So this comes as it is. Let me plug in beta equal to 0. So what will I get? Here I'll get 1, 0, 0, 1. And essentially this multiplication is going to give me a vector out of which I have to see the first component. The first component. It will give a 1 by 2 vector, a 2 by 1 vector, out of which I have to see the first combination because that is the intensity of light that is coming out of the analyzer. Okay, so let us rearrange this a little bit. Let me take this to the front. Let me also take this to the front. So what happens here? 1 by root 2 into 1 by root 2 becomes 1 by 2. Very well. So this is what I have to multiply now. So let me multiply one after the other, keeping this the same. I don't need to expand this because whatever the background light is coming, I just need to find out whether it will be transmitted or cut out totally. So I just keep it like that. And then let me multiply these two quantities. So what does that come out to be? This will be minus I and this will be 1 into this quantity. Now let us multiply these two. So this will be just as it is. Sorry. This will be just as it is. So this is minus I plus I. And this will be minus I squared plus 1 is what we are getting from this multiplication. And then this comes as it is here. Okay, so what does this come out to be? Minus I plus I is 0. I squared is minus 1. Minus of minus 1 is 1. So I have here 2. So this is what I get. And then let me multiply this out. So this will be 1 into 0, 0 into 2. So this is 0, 0 and 1, 2 into KEI omega t. So what does this come out to be? This will be 0 and 1 KEI omega t. And I know that this is nothing but E along minus beta and E along minus beta plus pi by 2 is what this is, this quantity is. So what does this tell us? That no matter what intensity I pass along the analyzer, out of the analyzer, there is no light coming in, no light coming out. In such a case, this combination, when both are crossed, gives me dark field. So this is a dark field arrangement. So this is dark. Similarly, if let us say I keep everything the same in this problem, I keep everything the same. Only what I do, the analyzer, I make it parallel to the polarizer. So what would I have to substitute for beta actually? In beta, I will have to substitute 90 degrees. In which case, what that will mean is I have to read the second column, the second component of the vector rather than the first. Because first component is E along the analyzer. Second is E along the analyzer plus pi by 2. Now what I have done is if I make the analyzer parallel, to the polarizer. Essentially, I'm looking at this element, and here I see the entire light that comes get passed just like that. So what can I conclude from this? From this analysis, I can conclude that this was crossed. Similarly, when the quarter wave plates are crossed, but the analyzer and polarizer are kept parallel. In such a case, this will be a bright field because K I E omega t passes as is. Similarly, using a similar logic, you can attempt these two. Essentially, what this will come out is when both are similar in nature, when both are crossed, analyzer and polarizer is crossed as well as quarter wave plate is crossed, it will be dark field. Or if this is parallel and that is also parallel, this will be dark field. If that this thing is disturbed, then it will be bright field. But these I encourage you to solve once for yourself the way we did it using matrix multiplication, so that if you do it a couple of times at least, then you won't have to depend on memory. Quickly you can attempt and multiply them out and see for yourself. So I hope this is clear. If there are any questions, please feel free to ask. Okay, so I take it that this is clear. Very well. So let us look at this question. A model loaded in a circular polariscope arrangement. So we have already been given that it is a circular polariscope where we are able to see there is quarter wave plate, two quarter wave plates, out of which first one slow axis is at 135. Here we took the first one's slow axis at 45 degrees. Where is it? Here we took the first one at 45 degrees. There it is at 135. 1 minute. There seems to be a lag here. Just a moment. Okay. There was a slight lag between the screen. That is why I had to stop it. Okay. Anyway, in that same way we have developed this, you can try one of the combinations out and see. Yeah, sorry, we were looking at this question. A model loaded in a circular polariscope arrangement is shown in the figure. At a point X in the model, the fringe order is found to be 3. The fringe order is found to be 3. Different regions are marked. Identify the state of polarization of light passing through point X. At each region, enter the appropriate region. Enter the appropriate letter ABC indicating the state of polarization. Okay, so the state of polarization is given like this, and we can see that this is polarizer. This is the fast and slow axis. Then we have the fast and slow axis of the model like that, and we have been given that the fringe order there is 3. Then we have the crossed combination of the quarter wave plate, and then we have the analyzer at 0 degrees. So in region 1, we know that it is plane polarized light. So if that is plane polarized light, then region 1 would be A. Then we have a quarter wave plate. We have a quarter wave plate which introduces a retardation of delta by 4. Lambda by 4, sorry. Which introduces a retardation of lambda by 4. And the orientation is kept such that the plane polarized light that passes gets equally split. The amplitudes remain the same. In such a case, we have circularly polarized light.
So we have circularly polarized light. Then it passes through our point, some point. This is the point where it is shown. So I'll take that point X, where the fringe order is found to be 3. So if fringe order at X is found to be 3, this implies that delta by 2 pi is 3, which means delta is 3 times 2 pi. So it is 3 wavelengths, essentially speaking. The retardation is 3 wavelengths. In such a case, now if we see a sine wave, for example, if this is retarded by 3 wavelengths, essentially nothing changes in this. It still remains the same. So what happens is, since the fringe order is an integer fringe order, in region 3, the model behaves like a full wave plate, in which case the light is still circularly polarized. It won't be so in case the retardation was not an integer multiple of the wavelengths. If that was different, then there would naturally be some modification. Then from here, what we are seeing is light was passing like this. Then from here it became circular. Here also it became circular. Now we are just trying to negate what was done in order to whatever was brought in by the quarter wave plate, we are just placing a cross combination so that it gets negated. So essentially in region 4, it is plane polarized light again. And it gets negated, and it is still, the plane of its polarization is still like that. And we have placed an analyzer that is perpendicular to it. So what will we see in region 5? Region 5 will give me no light, which is another way to say that at that point X there is a fringe, because a fringe gets formed a black pattern, and this is a dark field arrangement. So I'll be seeing just a black, or rather a fringe at point X. So that is what this implies. I hope this is clear. If there are any questions, please feel free to ask. Okay, so I take it this is clear. Okay, so let us look at this question. It is decided to find the fringe order at a point in the model using Babinet-Soleil compensation technique. Steps to be followed are given in the letters. Enter the letters without comma or spacing. Arrange the steps suitably. So one difference between this question and the previous one on finding the isoclinic angle is that there we had to shortlist first which of them form part of our steps and then arrange them. Here it is just that we have to arrange them suitably. Okay. So here first we have the model. I won't draw it timeline again. Maybe I'll just take it from there. 1 minute. Let me take this one. Yeah. So I have it like this at some point. Now, initially what I have to do in that compensation technique is there'll be some isoclinic fringe somewhere. I'm just considering that isoclinic fringe is over here and not on the point of interest. So what I do is I rotate this I rotate the crossed combination such that the fringe now passes through this point. The fringe now passes through this point. So this angle I know is theta at that point x. Let me call that point, let me call this point of interest as point x. Now, once I know theta, I take the Babinet-Soleil compensator. I rotate it at that very angle. Essentially, I keep it parallel to my analyzer and keep it there. It won't be this big. It'll be something like that. So I'll keep it there. Then I'll start rotating the knob till I find the fringe, isochromatic fringe, of known fringe order pass through that point. Once I do that, I will have a reading over here. There will be a dial which will give me a reading. And I have to compare that reading against their calibration chart and find out what the isoclinic angle is. So this is the entire process. So let us read the options. Align the compensator at the isoclinic angle. Rotate the knob of the compensator until a fringe is seen. Find the isoclinic angle at the point of interest. So essentially, we have to first find the isoclinic angle for us to align it with the isoclinic angle. Note down the counter reading, find out the fringe order. So first step is to find out the isoclinic angle, which we have done using a polariscope, plane polariscope. Next, we rotate the knob. Next, we align the compensator at that isoclinic angle. Then we rotate the knob in order such that the fringe passes through the point of interest. Once we have done this, we have a reading in our equipment. We have the reading that is representative of some constant of some relation with the retardation brought about. And from there, we find out the fringe order from the graph supplied by the manufacturer. So this is step E. So if we do it in this order, we'll be able to find what the uh, retardation or rather the fringe order is at that point. Instead of using an external element, if we simply use Tardy's method of compensation, we can simply rotate the analyzer and find out what our uh, this is, what our fringe order is, what is the retardation that we have brought about. So that is the way we do this. Okay, so let us look at this question. Mention how to estimate the stress concentration factor from photoelasticity data. Photoelastic data. The figure shows a pattern observed for a finite plate of dimensions length. Let me take this itself as the length, this itself as the plate, rather than considering it that it's very big. It is actually this size only because this is given to be 36 mm and the whole dia is given to be 12 mm, which seems to be one third of that. So that adds up. This is 12 mm dia and this is 230 mm. I'll just put like that. Okay. Hole diameter is this. Thickness is 6 mm for this case. And it is subject to an axial pull. So this axial pull is applied at both ends naturally. Okay, it is applied like that. But let me not show it here because it is blocking my text. So it is applied with an axial load of 288 Newton. Fine. The far field fringe order for the load is found to be 0.86. So what does that mean? Far field means that we have the plate like that, and then we have the hole here, and it is subjected to tension like that. So far field is sufficiently far away from this discontinuity, because at this discontinuity, if this discontinuity was not there, it is just a plate under uniform tension. It will have the same fringe order everywhere. Whereas this is leading to some stress concentration here. So sufficiently away from this, we will essentially be seeing uniform color, the distribution to be uniform. So that is what at that point we are somewhere they have measured, and the fringe order there is found to be 0.86. So N far field is found to be 0.86. Okay. Near the boundary of the hole, fringe order 2 was found. This is the hole. Let me, it's not very high definition. So let me just draw it once again. So this is the hole, and we have a we have a fringe like that. We have one fringe is like this, one fringe is like this, then other fringe goes like that. Same thing on the bottom also. So this is how the fringes look. Now, in that case, what we are saying is there is this fringe and the hole is this. This is the hole. Now this fringe order n equal to 2 near the boundary of the hole, the fringe order 2 was found to move and occupy the boundary of the hole when the analyzer is rotated by an angle 2.83 degrees is what is told. Now for this, essentially what we are saying is we have used Tardy's method of compensation. So in Tardy's method of compensation, once we rotate the compensate the analyzer, our essentially what happens is the fringe order, one of the fringes moves to that point because we have additionally added our retardation. I think before this, we can just have a brief, very, very brief discussion about Tardy's method also, so that things are clear. So what do we do essentially in Tardy's method of compensation is we have to, let us say there is light, and let us say I have kept the polarizer like that. 0, 1. 1 minute. Yeah, okay. So this is 0, 1. I have the polarizer kept like that. Now, what I do is I have my quarter wave plate. Let us say it is at 135 degrees. So it is at 135 degrees. Then let me move this here. After this, let me have my model. My model which will have cos delta by 2 minus I sin delta by 2 cos 2 theta minus I sin delta by 2 sin 2 theta. This is same. This is just the opposite. Let us say this is my model. Then I have another quarter wave plate. Since I cannot write it in one line because of space constraints, I'm writing it like this. And let this be crossed. So when it is crossed, I just need to put a minus sign there. Then I have my analyzer. And we saw analyzer, let it be at some arbitrary angle beta. So this will be cos beta minus sin beta, cos beta. And this is my E of minus beta, E of minus beta plus pi by 2. This is essentially the expression for my light that is coming. So again, let me group the 2's and multiply this out. So actually no harm in multiplying it out, but okay, let us do that. So this is as is, and then I have a 2 here. Then I have this. Then I have this. I have these two quantities here. And then I have, as usual, I have this here. So this is what I need to multiply out. Now, let us say that instead of doing this entire activity, first, what I did is I found out the isoclinic angle at that point and I aligned the entire polariscope to that isoclinic angle. Let us say it was 30 degrees, so I put the first polarizer at 90 plus 30 degrees, 90 plus theta, whatever that was. Second, first quarter wave plate, instead of 45, I put it at 45 plus theta. Then, like that, if everything I aligned, then what happens is this theta with respect to our benchmark becomes 0. So that simplifies our calculation. That is why we do that. So in that case, let us say the polariscope is aligned to theta p. In such a case, this comes as this. This will just be cos delta by 2 and this is aligned. This becomes 0 because theta sine 0. This will be cos delta by 2 plus I sine delta by 2 into this entire thing. Now if you multiply this out, essentially what we will get is, because it's the expression for circular polariscope, that is why I know this. So it will be sine delta by 2 into cos 2 theta minus I sine 2 theta, and then this will be cos delta by 2. This is what you get in the case of a circular polariscope where the isoclinic angle is theta with respect to the datum. But here, since we have changed the datum, our theta is essentially 0. So this quantity doesn't even appear. So this quantity doesn't even appear. It simply becomes this into our cos beta minus sine beta, and cos beta. And we have the 1 by 2 here. Okay. Actually, this 1 by 2 will get absorbed when we multiply that. That is the way it will be. If I encourage you to multiply this once and check this for yourself, it will come out to be this. Okay, so what is this expression give us? Actually, it gives us this quantity. It gives us this quantity. So let us multiply this out. This is cos beta sine delta by 2 minus sine beta cos delta by 2, and then this will be sine beta sine delta by 2 plus cos beta cos delta by 2. But we are only interested in the first quantity, since that is what comes out as the light out of the analyzer, as we discussed before. So what will that be? So E, so light from analyzer is nothing but E minus beta, which is this expression. I don't want to write it again. I'll just copy this. It is this. So this much we have found. Now what we have to do is, let us say that it is passing through a fringe. What this implies, what this entire thing implies is, in a circular polariscope, oriented at the isoclinic angle at the point of interest, the light that comes out of the analyzer kept at beta from the datum. So once I have aligned my circular polariscope to theta p, which I found initially. Once I did that and put my analyzer at beta degree with that datum, this is the light that comes out at me after the analyzer. So this is what compensation is. What I try to do is, I try to rotate the analyzer. In other words, I try to change beta till a fringe passes through that. What does a fringe passing mean? It means that the intensity becomes zero. So essentially what I do is, I put this zero and try by changing beta, I make this zero. Meaning by rotating the analyzer, I make a fringe pass through this point. So condition for the fringe to pass, E of minus beta equaling 0, this gives me what? This gives me this expression equaling 0. This equal to 0 implies that tan beta is tan delta by 2, or in other words, beta is nothing but delta by 2. So we can see delta is the retardation. By rotating the analyzer by an angle beta, I am able to impart the same retardation, which is not from the mechanics of the problem. I have introduced that. So that is what we mean by compensation. We are compensating for the additional retardation so that the fringe passes through that. So I hope this is clear. This is the background behind Tardy's method of compensation. Now with this, if we try to revisit our problem, what did the problem say? It said that near the boundary of the hole, the fringe order 2 was found to move and occupy the boundary when the analyzer was rotated by 83 degrees. I rotated the analyzer by 83. Instead of the fringe point being here, it moved to this point. So naturally, from the mechanics of the problem, I know that stress here and stress here are different. Stress near the hole is much higher. So in such a case, if I rotated the analyzer, imparting it artificial or compensating for the retardation, the fringe order 2 moved here, means that the fringe order at that point would have been actual fringe order at that point would have been 2 plus the retardation brought about by the compensator. Rather, let me not write 2. Let me write, see, n is delta by 2 pi. So, delta is 2 pi n. So, the retardation brought about for 83 degrees beta. What is the retardation that has been brought about? Is 2 beta, which is 83 into 2. 83 into 2, it is 166 degrees. The retardation is equivalent to 166 degrees, which implies it is 166 pi by 180 radians. So this is the artificial retardation that has been brought about. Now, at that point, at the neighboring point, fringe order n is already 2, which implies it is 2 pi into 2 is the retardation at that point. So the total retardation would be 2 pi into 2 plus this 166 by 180 pi. This will be the total retardation, but we want to essentially find out the fringe order. It will just be the total retardation by 2 pi, which is 2 plus 83 by 180. I hope I actually went a little I bypassed the general explanation and came here so that from first principles also you are able to reason out why this is. I hope this is clear. It doesn't create any confusion. So it is 283 by 180 is 0.46 plus 2. So this comes to 2.46. So what this implies is, for this problem, I had a fringe order 2 at this point. Then I rotated the analyzer by 83 degrees and that second fringe order appeared to come here, which means I added the additional retardation. From my compensation knowledge, I have found out that the fringe order there is actually 2.46. Instead of 2, it is much higher than that. It is 2.46. So n at the hole Total fringe order at the boundary of the hole, we have found this out to be 2.46. 2.46. I hope that is clear. Next part is asking what is the stress concentration factor. So stress concentration factor is defined as N at the hole by N far field. Let us also briefly see why this stress concentration factor, what does it mean? Essentially, if we take a plate that is uniform without any defect or a hole and we apply the load, our fringe order for this load should have been 0.86. That is what this data tells us. The far field fringe order is 0.86. This is how it should have been, ideally. But because of the introduction of this hole, yes, sir. Yeah, please go ahead. Good evening. Okay. Yeah, I'll just complete this and perhaps then you can take it up. Then we can take it up. Yeah. Okay. So ideally it should have been 0.86, but because of the introduction of this hole, we have got the stress shoot up to a higher value. So this SCF is just a measure of how much it gets magnified. So 2.46 by 0.86 is 2.86. So 2.86 is the magnification that is brought about, which is the stress concentration. Stress is getting concentrated at that point. So I hope this is clear. This is just the last question. Let me address this and then we'll take up your question, sir. It is required to find the fringe order at point X. At this point, it is required to find the fringe order uh, in the boundary of a hole in a plate subjected to tension. The fringes observed under monochromatic and white light source are shown in the figure. Okay. Okay, perhaps only one is shown. Fine. To find the fringe order, Tardy's method of compensation is used. At the point of interest, the isoclinic was found to be 0. The isoclinic angle is 0 at that point. That is given. When the analyzer is rotated by 45 degrees from the reference axis, a fringe order emerged from the boundary and reached out to the point of interest. So essentially we have, since this is a solid continuum, if this is fringe order 3, we know that the gradient of the fringe order is like that. Stress gets concentrated more here as compared to somewhere here. So the stress is climbing that way. So if this is 3, then naturally the next fringe order, this this would have to be 4, in which case this would have to be 5. Now what the question says is they rotated the analyzer. The entire circular polariscope is at 0 degree only, and that happens to be the isoclinic angle here. Now when this is rotated by 45, a new fringe order emerged from the boundary. So 6 would have been somewhere, that is 6 came into the domain when the thing was rotated by 45 degrees, which means 3 would have gone here, 4 would have gone here, 5, and then 6 would have come there. That is what this implies. Okay, with this background, what is the closest fringe order to the point X? It is given 6 is what came. 6 is the integer fringe order. That approached, or rather occupied, point X when rotated by 45 degrees. Let us say if we were to rotate in the opposite direction by 135 degrees, what would have happened? The fringe order 5 would have gone there. So which one is it close to? Is it close to 6 or 5? This is 5, this is 6 essentially. So the fringe order is somewhere between these two. When they rotated by 45 degrees, it reached this. when I rotate by 135 degrees, it reaches that. So my fringe order is somewhere over here. So it is closest fringe order, integer fringe order to that is fringe order 6. What is the fractional fringe order at this point of interest? Fractional fringe order is nothing but this quantity. What we added as the compensating fringe retardation is what is a fractional fringe order. So this is nothing but we rotated it by 45 degrees and we have to normalize this. So this is 180 and this will be minus. Why? Because the actual fringe order n actual is less than 6 and it is greater than 5. So my fractional fringe order has to be a negative quantity so that I add it to 6 and get where I am. So this is what it is. So it will be minus 45 by 180 is 1/4, of course, 0.25. So the total fringe order n total is n neighborhood plus the fractional fringe order, which is nothing but 6 plus minus 0.25 is equal to 5.75. So that is the fringe order at that point. Based on Tardy's method of compensation, we have found that. So I hope this is clear. Anyway, now I have run out of questions. Yes, sir, we'll take up your questions, Mr. Sahil. Okay. Yeah, fine. In brittle coating techniques, what is it that you want to know? Why X and Y? No, see, if there is, let us say that you have a brittle coating and it cracks. So essentially what that means is the coating is brittle, so it has to fail by maximum principal stress. So the direction of the crack, the orientation of the crack essentially gives you one of the principal stress directions. And the direction perpendicular to that gives the other principal stress direction. From your knowledge of the fact that it has cracked like this, you can figure out which is the maximum principal stress direction and which is the minimum. Right? Yeah. Yes. Yeah. Yeah. A distance is actually immaterial essentially because we don't consider any loss between the two. In actual polariscope setup, distance would be enough for you to comfortably change the angles. But essentially, distance between these optical components is not consequential in our calculation because we take it that there is no loss of light between the source and the point at which it impinges on the model and from the point where it exits the model to our sensor. So we don't consider any loss, and to a large extent, it is true. It holds good. No, no, it is not about that being loaded. See, essentially, loading, what the principle of Moire is independent of its loading. We have exploited the principle of Moire to measure displacement because from one frame to the other, when it is loaded, there is difference in the pattern. Moire essentially is due to mechanical interference by the virtue of that very pattern. Even if it is unloaded, that pattern comes. Now the thing is, yeah, yeah, it represents the interference of light that is passing through that grating. And as that thing is getting, for example, if we have two grids that are overlapping each other, light is coming at you in one particular form. There is interference, and because of which you see one pattern. Now, what we did to exploit this in stress analysis is the second pattern that was behind. We pulled it so that changed. So from one frame to the other, there was difference in the pattern. So Moire method applied to stress analysis essentially looking at the difference, change in the patterns as a function of time. But essentially, the principle behind the formation of pattern is independent of our stress analysis. It is by mechanical interference. Similarly, the very fact that birefringence happens is independent of our stress analysis.
It so happens that once we have noticed that physics, we are finding some materials which are exhibiting this property and we are utilizing that. Yeah, polarizer is polarizer is represented. Yeah, it is the it is the y-axis, no? In this case, if we have our x and y coordinate system like that, and if we have a vector that is like that, this graduation is 1. What are the components of that vector? It is 0 I cap plus 1 j cap, which can be represented as 0, 1. 1, 0. But essentially, because of the matrix multiplication, you cannot take 1, 0 and multiply it with this quantity. So that is why we go for 1, 0 transpose. So this is 1 zeros transpose you have to do in order to extract that quantity. This is what I explained as this. It will not change the orientation of the vector. It still remains the same. It is just a matter of multiplication of matrices. So this will be cos theta minus sine beta, cos beta, what I said. So this is what it gives. And the first component of that is your 1, 0. So that is what represents the light that comes out of the analyzer. It See, if actually, if you see this course, it is a compilation of so much of literature because each method itself has multiple books in itself. So I would rather suggest that if you are particular about one method, then perhaps you can confine yourself to that because to confine all the experimental methods into a single semester course itself is a big challenge. That is why professor has gone deep into transmission photoelasticity and strain gauges, coating techniques, these three. Others, he has given the base, but we have not delved much into it because of the time constraint. So it would essentially depend on which experimental technique you are trying to go deep into. And for those particular books are already mentioned in the lecture. You can see, I think it is lecture 2 or 3. You can just take a look there. There it is mentioned. Yeah. Yes. Thank you. Thank you. Thank you. Okay, perhaps today we have seen basics of circular polariscope, compensation techniques, and how to find out the isoclinic angle and isochromatic fringe order at any point of interest. Now, the idea behind this compensation technique is that for every point we rotate the analyzer, bring the fringe order to that point, and then try to figure out what the fringe order would have been. And this is cumbersome. And this again becomes a point by point technique. So the idea why this is important is so that we understand how the methods have evolved. Now there are methods like 3 fringe photoelasticity, TFP, 12 fringe photoelasticity or total fringe order photoelasticity, however you call it. That basically gives you the fringe order at every point in the domain by color matching. Similarly, there are phase shifting techniques with which at once you can get the isoclinic angle as well as the isochromatic parameter, meaning delta, throughout the domain of interest. So these methods have evolved over time and they are matured and quite applicable to many practical problems also. But this is how the conventional photoelasticity started. It is good to have the basis of Tardy's method of compensation and Jones calculus so that as we delve ahead, it will be beneficial for us. So that was the idea behind discussion of this week's question. So anyway, now I have run out of questions. So in case there are any further questions, you please feel free to ask. I'll try to address them. If there are no further questions, we can consider calling it a day and we'll try to discuss whatever forms part of week 6 in the next session, which will be held next Monday. Okay. So are there any other questions? Okay. Well, if there are no further questions, then perhaps we'll call it a day. I'll see you people next week. Thank you. Thank you. Thank you. Thank you. Thank you. Good day.